Distributed tracing is a technique used in the context of microservices architecture to monitor and analyze the flow of requests as they traverse multiple services in a distributed system. Understanding the interactions between services is crucial for diagnosing performance issues, understanding system behavior, and optimizing overall system performance. When a single user request is processed, it often involves multiple interconnected microservices working together to fulfill that request. Distributed tracing helps track the journey of a request through these services, allowing developers and operations teams to gain valuable insights into how the services collaborate and identify potential bottlenecks or errors. This is particularly useful in complex systems where a single request can trigger a cascade of events that span multiple services. To implement distributed tracing in our system, we usually assign a unique identifier to each request and propagate it through the system as the request is processed. This identifier is called a trace ID. Since trace ID is going to be passed along with the request, it can be used to correlate all the logs and events generated by the services involved in processing that request. We can then use tracing systems to visualize the entire trace, understanding the latency between services, identify bottlenecks, detect errors, and optimize performance. In this lesson, we'll focus on how to automatically generate trace IDs and propagate them through the system in our Nest.js applications. To begin, let's create a new library called tracing using the Nest CLI. Let's open the newly generated tracing service file and add the following code. This method simply generates a random UUID that we'll use as our trace ID. We need to assign this ID only once, when the HTTP request hits the application or when a cron job is triggered. Once we have the trace ID, we need to propagate it through the system so that it can be used to correlate all the logs and events generated by the services involved in processing this request. In this lesson, we'll focus on adding tracing to our alarms generator events processing pipeline. So let's head over to the alarms generator service file and update the generate alarm method to generate a trace ID using our new tracing service and attach it to the message headers under the trace ID key. Note that to construct the headers object, we use the nats headers function as we're using nats in our system, but if your system was using something aside from nats, you'd want to use the equivalent functionality there. Now, to make the tracing service available in the alarms generator module, we simply need to import the tracing module, so let's go ahead and do that now. And perfect! With all this in place, we can now switch our focus to the alarms service. Our goal now is to make sure that the trace ID is propagated through the system when the alarm service processes the message. Also, let's make sure to automatically write the trace ID to the log messages. So let's create a new tracing logger class that extends the default console logger class and overrides the format context method for us. To achieve this, let's create a new file in the tracing library called tracing.logger.ts and add the following code. And let's break this class down. First, we need to inject the request context and inquirer objects. The request context object represents the execution context of the incoming request, which we'll use to extract the trace ID from. Here, we assume that the logger will be used only by services that use the nats transporter. The inquirer object contains the host object, which we'll use to extract the name of the class that's using the logger. So for example, if we use the logger in the alarms service, the inquirer object will contain the alarms service instance. And likewise, if we inject the logger into the alarms controller, the inquirer object will contain the alarms controller instance. This means that our logger provider will not only be request scoped, but also transient scoped, which means that a new instance of the logger will be created for each class that uses it. Now onto the format context method. Here, we need to extract the trace ID from the request context and append it to the log message. Finally, we need to register the tracing logger as a provider in the tracing module. So, let's open up the tracing module TS file and add the following code. Excellent. With this in place, let's navigate to our alarms service and update the alarms module file to import the tracing module. Next, let's head over to the alarms service controller file and update it to inject the tracing logger, replacing the existing local logger instance. Let's save our changes, head over to the terminal, and start everything up with Docker Compose up. Once the application is up and running, let's wait a little bit and observe the logs. As we can see, all logs in the alarm service controller contain a trace ID now. Great. However, our trace ID is not yet propagated to the alarms classifier and notification services. So let's go ahead and fix this now. For this, we'll create a new client proxy class that internally updates the message headers with the trace ID before publishing a message. So let's generate a new module first called nats-client. And let's make sure to select the tracing library as the module's destination. Next, inside of this module, let's create a new file called constants with the following content. This file simply exports a constant that will represent the NATS client provider. Next, let's create yet another file and call it nats-client.proxy with the following content. As we can see, we're injecting the client proxy instance, which represents our message broker, and the context object into the constructor. We'll use the client proxy to publish messages to the message broker and the context object to access the trace ID that we attached to the message earlier. Also, the NATS client proxy class is marked as request scoped, which means that a new instance of this class will be created for each incoming request. This is important because we want to make sure that each request has its own instance of the NATS client proxy class. Next up, let's add a new method called setTraceID that will be responsible for updating the message headers with the trace ID. Here, we're checking if the message is an instance of NATS record or not. If it is, we're creating a new instance of the NATS record builder class and updating its headers with the trace ID. Otherwise, we're creating a new instance of the NATS record builder class and updating its data and headers with the trace ID. Finally, let's add new methods called send and emit to mimic the client proxy API. Last but not least, let's open up the NATS client module file and register this NATS client proxy as a provider and make sure to export it. Also, let's not forget to import the clients module here with the exact same configuration we have in other applications. Great. With this in place, let's switch back to our alarm service and update the alarm service module file to import the NATS client module. You can also remove the NATS configuration from the client's module array. Last but not least, let's update the alarm service controller file to inject the NATS client proxy instead of just client proxy. Just before we test everything out, let's also update the alarms classifier service to use the tracing logger instead of the local logger instance. So let's open up our alarms classifier service module file and import the tracing module there. Next, let's open up the alarms classifier service controller file and replace the local logger instance with our new tracing logger. Let's save our changes, head over to the terminal, and take a look at those logs. As we can see, the trace ID is now propagated to the alarms classifier service as well. Fantastic. The last missing piece is the notification service. However, it uses RabbitMQ instead of NATS, so we would have to create a new Rabbit Client Proxy class that would be similar to the NATS Client Proxy class we just created. As this would be a lot of repetitive work, we won't be doing this in this course. You can think of this as a homework assignment if you want to practice your skills and do it yourself. So, to recap, distributed tracing is a powerful tool that enables developers and operations teams to gain deep insights into complex microservices architectures. We now have all the basic elements set up ourselves that could be used in any real-world Nest.js microservice application you work on in the future. Distributed tracing is so beneficial in microservices as it promotes better understanding, smoother debugging, and more efficient performance optimization, making it an essential part of building and maintaining resilient microservices-based systems. For production applications, consider using more sophisticated instrumentation tools such as OpenTelemetry in combination with Jaeger for visualization and analysis. These tools provide a more comprehensive solution for distributed tracing and can be easily integrated with Nest.js applications. And that's all for this course, but thank you again for being here, supporting Nest.js, and learning Nest with us. We hope you learned a lot with this course. Make sure to check out the entire catalog of courses to learn everything else from advanced techniques to Nest fundamentals. See you in the next one.